Hello, everyone. We're going to talk about chapter 8.6 today, which is rational exponents and radical expressions. So, this has to talk about rational exponents. So, remember rational numbers. Rational numbers include normal numbers you typically see like 0, 1, 2, 3, etc. But they also include negative numbers. So, negative exponents like something to the -1 power, something to the -2 power. But it also includes fractional exponents as well. X to the 1/2 power, 13 to the 3/5 power, some crazy stuff like that. What we're going to be doing is we're going to be converting things from exponent form, quote unquote, to radical form. And it's really not too tricky, but there's something I want to let you know going into this about radicals. So we've seen things like the square root of 25 in the past, right? Now, you may have also seen something in the past where you've got the cube root or third root, you can also say, of a number, or maybe the fourth root of a number, right? You might have seen those before. Now, what this number on the outside means is it's called the index number, and it's essentially the exponent of the term that you're looking for. So just to give you kind of a background, if you didn't already know this, if you already know this, then that's good. But if you didn't, at least you kind of know now. When you take the cube root of 27, what you're essentially asking is what number would you take to the third power to equal 27? And for the fourth root of 64, it's what number could you take to the fourth power that would equal 64? So normally when you see a square root, we're asking what number do I square to equal 25 or whatever. So just keep in mind that's what the index number is indicating when it's solving that problem. That's what it's there for. It's what its purpose is. But what I really want to point out is the fact that for these two, let me get a different color, right? The 3 and the 4, we wrote them there. Why didn't we write a number here? And even though we don't write a number, does that mean that there's not a number? Or what's the index number for this square root of 25? The 3 and the 4 here are pretty obvious, and they have to be written there. Why don't I have to have an index number on the 25? Well, first answer is that the index number is there, and that index number is 2. It's not 1. Typically, we see a lot of invisible 1s in math, but here we have an invisible 2. The reason it's 2 is because, like these are looking for what cubed and what's to the fourth power, this one's looking for what goes to the second power. So that's why it's a 2. And the reason we don't write it very often is because we use it more often than anything else. So we typically talk about square roots a lot. And because of that, we don't want to, we get kind of lazy as math people. And we don't want to have to write that 2 as an index number there all the time if we're going to be encountering it so much. We'll just kind of say, you know what, hey, just when I don't write it there, just assume it's a 2. So that's kind of the laziness behind it. But it is technically a 2 there. So anytime you see the square root of 81, or the square root of anything, right, just remember that there's secretly a 2 chilling out there, okay? All right, so I just wanted to fill you in on that first. Now, what we're going to do is convert rational exponents, so exponents that have fractions on them, or exponents that are fractions, into radical expressions. So you'll see them kind of illustrated here. It's really a simple thing because all it is essentially is you're just relocating the numbers that are in the exponent into the radical, or relocating them from the radical back to an exponent. So it's just more of a rearrangement kind of thing than anything else, but it is one that you want to be familiar with, something you want to know about. So you can kind of see in these examples sort of how it works. I think this bottom example here with 8 to the 2/3 is the most obvious. But the quote-unquote m piece, which is our numerator, 2, is the exponent when we have it in radical form. And our denominator piece, which is 3, is our index number in radical form. So we want to remember that. Our numerator is our exponent, and our denominator is our index. It also, just pointing out now, it's not really going to matter. You can kind of see the two similarities between these at the bottom. They're pretty much the same thing. If the exponent is outside the radical or inside the radical, which is the only difference there, it really isn't going to make too big a difference. I don't know if one is technically more simplified than the other. I think they're both kind of the same, to be honest with you. And the reason that it doesn't really matter is because exponents and radicals go together. They're sort of tied together, like multiplying is tied with division and adding is tied with subtracting. So it doesn't really matter the order that you do those things sometimes when they're tied together like that. So it's not really going to matter if it's inside or outside. So just kind of keep that in mind. But take a long look at that. We're going to try a few out on our own. All right. So here, go away. Here, write each expression by using rational exponents. So we're going to convert it from radical form into exponent form. So remember the rule was, I forget if it was m over n. Yeah, it is. So a to the m over n power is the same as the nth root of a to the m power. So the m, which is our exponent piece, so you see that here, right? M is our exponent piece. That makes 4 the m. And the n is our index piece, which makes 8 the n. So if I want to convert this into exponent form, it's pretty simple. I have a is the base, obviously, and 4 is my numerator, 8 is my denominator, right? Because that's where the m and the n go. So there you have it. That's our exponent form. Now, a simplified version of this is a to the 1/2 power. Okay? And that's your exponent form, your simplified exponent form as well, or rational exponent form, however you want to say it. So in part B, it's the same thing, same story. F is the base, 15 is my m, which makes it my numerator, and 5 is my n, right? So it's going to be 15 over 5, which is the same as f to the 3rd power, right? 15 over 5 simplifies to f to the 3rd power. All right. It's as simple as that. It's just really just relocating some of those numbers. Not the most complicated thing in the world. We're not really doing math. We're just sort of conversions in a way. But there is something I want to talk about before I move on to the next slide, and that's this 1/2 power thing. So one thing you want to kind of know, just memorize it, just know it as a fact. Like, 2 plus 2 is 4. You don't really have to add 2 and 2 together. You just always know 2 plus 2 is 4. Something you just always want to know is that when you have something to the 1/2 power, it's the same as the square root of that number. Because essentially what you're saying here is 1 is the m, which means it's the exponent, which x to the 1st power is the same as just x, right? And 2 is the index, which means you're doing a square root, which again, you don't always see the 2 there when you have the square root. So the conversion works. You have a 2 and a 1 there, but typically we don't see those 2 or that 1 there. We just see the square root of x. So anytime you have something to the 1/2 power, just remember that it's always a square root. So if you have 16 to the 1/2 power, remember that that's just the square root of 16. If you have y to the 1/2 power, then you just have the square root of y. If you have anything, okay, anything at all to the 1/2 power, then you just have the square root of that thing, okay? So 1/2 is a very important and probably the most common and typically used rational exponent, because it's the same thing as a square root, and we know how much we use square roots. So just keep that in mind. All right, let's try a few more of these out. So remember, the m is the numerator of the rational exponent, and 4, the index here, is the denominator for it. So this is the same as x to the 3 over 4 power, 3/4 power. This one would be y to the 9 over 3, which is the same as just y to the third if you want to simplify it. And then here we have z to the 2 over 4, which is the same as z to the 1/2 power. Which, remember, that z to the 1/2 power is just the same as square root of z. So this is the same thing as saying square root of z. And again, that's just helpful to know. All right, let's talk about some of the properties that we have these exponents for. So when we multiply powers, we actually add those exponents together. So here you can see we're multiplying x to the second times x to the third, but we don't actually multiply the 2 or 3 together. We actually add the 2 and the 3 together. Now the reason for that, exponents are not the same as just your typical number. Exponents are there just kind of counting how many x's you're tying with, together. So when you have x to the second, you're saying x times x. Why does it keep doing that? X times x. And when you multiply it with x to the third, you're multiplying it with 3 more x's. So x to the second times x to the third. You can see that the 2 is just there to count how many x's you're putting together. So you have 2 x's paired with 3 more x's. So when you multiply them all out, you essentially have 5 x's, right? X to the 5th power. So you're adding kind of how many x's you're putting together. When you're multiplying the x's, yes, but the exponents, you're not multiplying. The exponents are just counting how many you're multiplying together. So dividing powers works somewhat the same way, except you subtract the exponents. And the reason for that is because they're canceling out. So you have x to the 5th over x to the second. You have some pairs of x's that cancel out, right? So you're taking them away, so to speak, or subtracting them, leaving you with, 3 left over that didn't cancel out. So you're just sort of subtracting them because that's how many would cancel out. So 5 minus 2 is 3. So kind of a simpler way of remembering it. Now, when you have powers raised to another power, an exponent on top of another exponent, exponentception, as you will, you actually multiply those exponents. And the reason is if you have x to the second, multiplying it by itself 3 times, so there's one version of it, times the second version of it, times the third version of it. You have x to the second multiplied 3 times, x to the second to the third power, then you're having, 3 groups of 2, which is why, as you can see here, why it becomes x to the 6. But the shorthand way of remembering it is that you would multiply those exponents together. So remember the difference between this when you add the exponents and that when you multiply them, because they seem kind of similar, but they're very, very different, especially when you get to larger exponents. Now, power of a product and quotient, these last two properties kind of go hand in hand together. They're pretty much doing the same thing. But what I want to remind you of is that this only is going to work for products or quotients, okay? When you're multiplying or dividing things. It will not work if you have a plus sign or a minus sign mixed in these parentheses. So if you have a plus sign or a minus sign, immediately remember that this property is not going to work. But if you have no plus sign, you have no minus sign, then it's as simple as just it's pretty much the same thing as this part, where you multiply them together because you have an exponent on top of another exponent. So you kind of just multiply them together. And you can multiply it to each piece inside. So it's sort of like distributing, if you will. But remember, it doesn't work if you have a plus sign or minus sign in there. It has to be a product or quotient only. It cannot be a sum or difference. And that's particularly helpful when you have properties like this. These fractions, it makes them a lot easier to simplify, by hand especially. So let's give it a go. I have here x to the 4th times x to the 7th. So I'm taking 4 x's and multiplying it with 7 x's. So that means I'm multiplying 11 x's altogether, right? Remember, you add those exponents. 1y tied with 5 more means you're going to have 6 of them all multiplied together. Here, even though it's a negative, it still means the same thing. This is z to the 3rd power because 6 minus 3 is 3. And then here, remember, you're still going to add these exponents together. So 7 ninths plus 11 ninths is really 18 ninths. So you have 7 to the 18 ninths, which is, as you might notice, 18 over 9 is 2. So 7 squared, which, if you want, you can go ahead and write as 49. Okay. So if you type that in the calculator, it should work if you type it in correctly. It should say 49, but we're doing this intentionally without a calculator because we want to know how to do it without a calculator as well. All right, here we got quotients. So remember, you subtract the exponents. So 5 x's take away 2 would be x to the third. This would be y to the second. 3 take away 5 would be z to the negative 2 power. And then 3/4 minus 5/4 would be, negative 2/4. So 16 to the negative 2/4, which is the same as 16 to negative 1/2. Now, something I want to say, though, before we move on about these negative exponents. We're not allowed to leave exponents negative. Okay, it's against one of the rules in math. So how do you convert it? How do you change the exponent to a positive? Well, the answer is you can't just change it to a positive all, willy-nilly. It's about conversions again. It's about relocations. So when you have something to a negative exponent, let me move this up here. 16 to negative 1/2. That negative exponent just means that number is in the wrong place. So for z is in the wrong spot. So remember, z to the negative 2, this is the same as z to negative 2 over 1, right? And this is the same as 16 negative 1/2 over 1. When it has a negative exponent, it means it's in the wrong part of the fraction. All you have to do to convert it to a positive exponent is relocate that z or the 16 or whatever it is to the other part of the fraction, and then it'll have a positive exponent. So let me just show you what I mean. So the z with the negative 2 exponent means it shouldn't be in the numerator, it should be in the denominator, which means I should have 1 on top and z on the bottom. Z to the positive 2 power. If z is in the right place, it has a positive exponent. So just relocating it to the denominator does the trick. Now, I just realized this, and I know a lot of you are thinking this. The 1 that was down here didn't move, okay? I didn't just flip sides. That's not what I did. The 1 is still technically down here, okay? It's just 1 times z to the second. So that 1 is the same as the one I just wrote. The reason there's a 1 up here is because there's always a 1 up there, right? Think of that as 1 times z to the negative 2 power. Well, that 1 stayed up there. It's one of those invisible things in math. If I actually had this as, let's change my example up a little bit. Let's say I had 3z to the negative 2 over 5, right? I'm not going to relocate the 3 or the 5. The 3 is going to stay where it is. The 5 is going to stay where it is. But the z is going to relocate because it has a negative exponent. So 3 will stay on top. 5 will stay on bottom. The z will move to the bottom as well, but it'll now have a positive exponent. So you're only moving the part that has the negative exponent, okay? Not switching the whole fraction around. So for us, the 16 is a negative 1/2. Again, that 16 is in the wrong place, so that 16 belongs in the denominator, and now it'll have a positive 1/2 exponent, which, remember, 1/2 exponent is the same as square root. So it's the same as 1 over the square root of 16, which we also know square root of 16 is 4. So we have 1 over 4. So when you write this, 16 to the negative 1/2 power, you don't really think, hey, it's going to be 1/4, but it really is 1/4. When you know these properties, it makes things a lot easier to work with. Who would have ever thought, just by looking at the original problem here, that it would have been just simply 1/4? So keep those things in mind. The whole reason we're doing these properties is because they're going to make things like this a whole lot easier if we know these properties and these rules. So remember, when you have an exponent on an exponent, you just multiply them. So here we have x to the third to the fifth. That's going to be x to the 15th. This will be y to the 14th. And then this will be z to the negative 4 power. But remember, We don't want to leave a negative exponent there. We want to move that z to the denominator, or it'll be a positive exponent. So 1 over the z to the positive 4 power. Cool? All right, remember you're still distributing here. As long as there's no plus or minus signs. So you see, I'm looking, and in none of those problems is there any plus or minus sign. So I don't have to worry about it. I'll just go ahead and distribute. X to the 4th to the 2nd would be x to the 8th. Y to the 3rd to the 2nd would be y to the 6th. This will be a to the 1st to the 3rd, which would just be a to the 3rd. B to the 4th to the 3rd, which would be b to the 12th. This would be f to the 10th over g to the 30th. I almost wrote 12 for a second there. I don't know why. G to the 30th. And then this one, I've got a lot of pieces, but it's all still the same. X to the 10th, y to the 6th, and z to the 8th. Now remember, if any of these had a negative exponent, I'd have to relocate it. All of them have positive exponents, which is fine. But if I were, for some reason, have z to negative 8 down here, then that would mean I'd have to move the z to up here where it'd have a positive 8. And that would have been my answer. So just keep in mind when you have a negative exponent, you're not really doing anything more than just moving it to a different part of the fraction. All right, if you want to take some time and try a few on your own, you certainly can. I don't know if I have the answers on this or not. I don't think I do. But you're welcome to give them a shot. Test your skills. Okay. I'm going to see if there's anything more I want to talk about in this one. Okay, so you know how we've written down our list of perfect squares in the past. Oops. Perfect squares, we know perfect squares are 4, 9, 16, 25, 36, 49, etc., right? Because 2 times 2, 3 times 3, 4 times 4, 5 times 5, etc. We want to kind of get used to our perfect cubes. We don't have to know them as well, but we at least want to know how to find them if we ever needed them. So 1, 8, 27, 64, 125, 216. That list goes on, but these are perfect cubes. We want to at least be able to recognize them when we see them. Because you're going to be asked, what's the cube root of 27? So that's essentially asking, what number do I cube that equals 27? And since 27 is a perfect cube, right, that number is 3. So cube root of 27 is just 3. All right, but what if you have the cube root of 54? Well, 54 is not a perfect cube. As you can see, it's not on this list here. Okay, but like simplifying square roots, we want to find what perfect cube goes into 54. And that answer is 27 goes into 54. Right? This is the same thing as the cube root of 27 times 2. So just like our square roots, we can break this up. So we have cube root 27 times cube root of 2. And then this, we already know, the cube root of 27 is a perfect cube. So that's just going to be 3. And then this doesn't simplify, so we leave that as the cube root of 2. So 3 cube root of 2 is kind of, I guess, the simplified version of that. So that's kind of a slightly better way of looking at it, I suppose. It's not the square root of 2, it's a cube root of 2. So make sure you've indicated that with that 3 there as the index. And then cube root of 40. 40 is not a perfect cube, but 8 is a perfect cube, and it goes into 40. So this is the same as the cube root of 8 times, what is it, 5? Yeah. So we know the cube root of 8. Cube root of 8 is 2. And the cube root of 5 doesn't simplify. So we would have that reduced to that. Okay, so same thing we did with our square roots, but with cube roots instead. So it's absolutely no different than when we did the square roots. You just have to know this list of numbers instead of this list of numbers. It's the same rules otherwise, okay? Now with exponents, it's pretty simple. Because remember, if you can think about it as converting it into radical form or exponent form, you have this would be x to the 6 over 3, which is the same as x to the second, right? Now notice what I essentially did was I just took the 6 and divided it by 3. 6 divided by 3 was 2. So I got x to the second. So it's really what's going to happen with all of these as well. 9 divided by 3 would become x. Well, I'll write it out first. We'll have 9 divided by 3. This will be y to the 3 divided by 3. This will be z to the 6 divided by 3. Right? That's just putting these as exponents and the index as denominator like we did earlier in the video. But a simpler version is just x to the third, y to the first, and z to the second. Now this one, we have a to the 5 over 3. This would be y to the second because 6 divided by 3 is 2. And then z to the 2 over 3. And that's it. Okay, it's the same thing as what we did earlier. It'll just have those exponents as rational numbers, fractions, and that's fine. All right. And last but not least, we got a handful here, but it's the same thing like we did when we did square roots. So break them all up. Cube root of 27, cube root of a to the 6th, and cube root of b to the 4th. So the cube root of 27 is 3. Cube root of a to the 6th is a to the second. And then that doesn't really simplify, but we convert it to b to the 4 over 3. So there's your answer for that one. Now, this is asking for the 4th root. So if we want to know the 4th roots, 1 or 2 to the 4th power is 16. 3 to the 4th power is 81, I believe. 4 to the 4th power, you probably want to start grabbing a calculator, is whatever 16 times 16 is. I think it's 200 and something. Let me grab my calculator. 256. Okay. These are perfect 4th exponent terms. I don't know. Perfect 4th roots or something. Anywho, we have the 4th root of 16, which we know is based on this is 2. We have 8 divided by 4, which would make that f to the 2nd power. 4 divided by 4, which would make that g to the 1st power. And then h to the 5 over 4th, which 5 over 4 doesn't simplify nicely, but we can just leave it as h to the 5 over 4. So the only trick there was knowing that 16 was a perfect 4th root, I suppose. But yeah. Now 5th root of 243, it's 243, a 5th root. Let's see here. I think it is. I think 3 to the 5th power is 243. So 243 is a perfect 5th root, because 3 to the 5th power is 243. So that means the 5th root of 243 is 3. We have here 7 divided by 5, so that'll be p to the 7/5. Q to the 15 over 5, which would be q to the 3rd. And r to the 9 over 5, which would be r to the 9 over 5. So that's the simplified version of that. It's not really hard, especially these exponent ones or these variable ones, because it's just kind of a fraction. 7 over 5, 15 over 5, 9 over 5. Simplifying if you can. The hard part was really the number. And that's just going to take maybe a little calculator to get used to, but you can handle it. All right, I'm going to end this here. I know it was a little bit longer than it should have been, but what you going to do? Good luck moving on. We'll talk about chapter 8.8 next one.